Hello ladies and gentlemen, and welcome to Distance Learning. Okay, so we're starting a new unit today. Our unit is on exponents. You've done exponents before, a tiny bit in grade 9, a little bit more in grade 10, a little bit more in grade 11. And so this is going to be called exponents for a unit. And I'm going to be using sheets that may or may not be the same to the ones that are in your notebook. So if they're not the same, go back, stop the video, and you can print out the new sheets if you want them, or you can just take notes on a separate piece of paper as we move on. So we're going to start off with something that should be familiar to us, are the general exponent rules, the very straightforward rules that we learn in grade 10. So let's first talk about a little bit, just because we should make sure that we know what we're talking about. If I have 2 to the 3, we have what's called a base of the exponent, and that's what's at the bottom. And we have what is called the exponent at the top. Now, to be honest, the whole thing should be called a power. Okay, the whole thing is a power, not an exponent. This little piece is the exponent. And what this power represents is 2 times 2 times 2, so that there are 3 2's multiplying together. So the exponent says take whatever the base is and multiply it out the number of times that the exponent's there. So we're going to remember for a second that if I have any old number like 2, it's the same as 2 to the 1. So it's just going to be 1, 2. But if you have 2 squared, then it'll be 2 times 2. And 2 cubed will be 2 times 2 times 2, and 2 to the 4 will be 2 times 2, and so on and so on. So, multiplying exponential terms. A to the n times b to the m equals a to the n plus m. Now notice the bases must be the same. If the bases aren't the same, then you have no business doing this rule. Okay, so it has to be the same base here, the same base here, and the same base here. And this is multiplying. So what that means is this is 3 to the 5 times 3 to the 4. So ultimately, 3 to the 5 is 5 3's being multiplied together. That is 3 to the 5. Then we have that multiplication in between them. And then we have 3 to the 4, which is 4 3's being multiplied together. So we have 5 3's from this one, and we have 4 3's from this one. And notice it's multiplying. So since the bases are the same, I have 5 of the base here times 4 more of the base here, which just goes to show you that it's going to be equal to the 5 plus 4 more, which is simply going to be 3 to the 9, which gives us this rule up here. So I have 2 to the 3 times 2 to the 2. You notice that the bases are the same, so the answer is going to have a base of 2. I've got 3 2's here being multiplied by 2 more 2's, so that'll be a total of 5 2's. This is in power. This is written as a power. It's a power of 2. It's called the fifth power. And it equals something. It equals 2 times 2 times 2 times 2. Now on your calculator, you should have a button that'll help you do that quickly. Mine's x to the y. So 2 is the base. Hit that button. To the 5 equals, and it equals 32. So what we know is 32 as a number can be written as a power of 2 to the 5th power. And 3 to the 9 equals 19,683 equals 3 to the 9. Now, you're starting to see that 3 to the 9 is a much easier way to go than calling it 19,683. However, 2 to the 5 and 32, you might think 32 is better to work with. But the equivalency is true no matter what you're talking about. They equal each other. Now, what if you divide exponential terms? So I have a to the n divided by a to the m. And another way to write this is simply a to the n divided by a to the m. And it led to this rule that you learned in grade 10 that you subtract them. Let's take a look at what's happening here. I have a to the 5, or 4 to the 5 on top. That is 1, 2, 3, 4, 5 4s. 4 to the 5 means 4 times 4 times 4 times 4 times 4. So there's 5 of them. 4 to the 3 is 4 times 4 times 4. Now we know that when we have division, we can reduce. I've got a 4 on top and a 4 on bottom. So it's the same as doing nothing. They're going to cancel each other out. They're going to cancel each other out. They're going to cancel each other out. What does that leave us with? 4 to the 2. So what we actually have here is we started with 4 to the 5 and we divided it by 4 to the 3, which means that I had 5 4s on top, 4 4s on the 3 4s on the bottom. Where are there going to be more 4s? So when I subtract them, where there's going to be more, 2 of them on top. So that's going to leave us with 5 minus 3, 4 to the 2. And the same's happening over here. We can do it a little bit quicker. So this will be 3 to the 7 divided by 3 to the 2, which is the same as writing it like that. Where are there going to be more 3's? On the top. When I go through reducing, how many more are on top? I got 5 of them on top. And now if you're concerned with me saying on top and on bottom, remember this had a bottom of just 1. We don't have to write it anymore. It'll just be 3 to the 5. Power of a power. So now what's happening is I've got a base to a power and the whole thing to a power. Well, what that means is 2 to the 3 is the base times 2 to the 3 times 2 to the 3 times 2 to the 3 4 times. That's what that means. That 4 means take the base and multiply it by itself, so there's 4 of them. Well, what that means is I've got 3 2's times another 3 2's times another 3 2's times another 3 2's. Well, that's going to be 3 plus 3 plus 3 plus 3 is going to be a total of 2 to the 12. Another way to think about that, if you did it a little bit faster though, is you're going to have 2 to the 3 to the 4. So how many 2 to the 3's are you going to have? 4 of them, 1, 2, 3, 4. And each one of those is going to give you 3 2's, so it's faster just to do the multiplication, but this is what's happening. So 9 to the 8, or 9 to the 3 to the 8 is going to be 9 to the 3 times 8, which is 9 to the 24. Now, let's just throw it in here because it's going to come up later. There's another way we could have written this, and that's not as this number. 9 to the 24 is a big number. Huge! Look at that. So it's this decimal times 10 to the 22. It's huge. So we're going to write it as 9 to the 24 and not like that because that's just nuts. But I'd like you to notice something. Notice that 9 is also equal to a power. It's equal to 3 squared. So we can substitute this 3 squared into the 9. So it'll be 3 squared to the 24, which will be 3 to the 2 times 24, which is 3 to the 48. So 3 to the 48 is equal to 9 to the 24. Now they have different bases, but when we expand them out, we get the same value. So that's something that we're going to keep in mind, that sometimes whatever our base is, it might be able to be taken to a smaller base, or a different base for that matter. Another quick example of that, just while we're talking about it, is let's say we look at 81. So 81 could be written as 9 squared, or it could be written as 3 to the 4. Now let's think about that for a minute. That would be 3 times 3 times 3 times 3. So there's 4 3's being multiplied. So any 2 of them gives you 9 times 9. So there's your 9 times 9 squared, and here's your 3 to the 4. See how that works? Okay. So let's take a look at what we have. We have some examples here that we're going to go through. So we've got 3 to the 2. So use the exponent rules to express each of the following as a single power. Do not evaluate, just as a single power. So no calculators really is what's happening here. So 3 to the 2 times 3 to the 5 being expressed as a single power. So the base is 3, they're the same, and I can take the exponents. So there's 2 3's here, 5 more 3's here, so that'll be 7 3's in total. Pretty simple. I've got 7 4's on top, I've got 2 4's on the bottom. Where are there more 4's? On the top. And how many more? 5. And if you're worried about top and bottom, that's the same as 4 to the 5 over 1, or 4 to the 5. And notice we're not evaluating these, we're not using a calculator, we're writing them as single powers. 2 to the 3 to the 3, well that is 2 to the 3 times 2 to the 3 times 2 to the 3, or if you remember your rules, it's 2 to the 3 times 3, which is 2 to the 9. 3 plus 3 plus 3 is 9, or 3 times 3 gives you 2 to the 9. Doesn't matter which one you use, just be able to do it. 2x squared to the 8. You got to be careful here because this is 2x squared times 2x squared times 2x squared times 2x squared. 8 of them. You got to be careful here. How many 2's are there? There's 8 2's being multiplied as well. So that's the 8 2's being multiplied. And x to the 2 to the 8 is the 16. This would be absolutely wrong if you wrote it like this. That's not what it is. You missed the 2. It was 2 times 2 times 2 times 2. There's 8 of them. You have to have that 2 to the 8. All right, this one over here. All right, so now we're going to do a little bit of work before we put the stuff together. So this is all multiplication. Another way to think about this is 4 being multiplied by a squared, being multiplied by b, being multiplied by 6, being multiplied by a, being multiplied by b cubed. Order of multiplication doesn't matter, so you can put the 4 and the 6 together. We can put the a squared and the a together, and we can put the b and the b cubed together. 4 times 6 is 24. A squared times a, well that's 3a's. B to the 1 times b to the 3 is 4b's. Now, you certainly don't have to do all of that work. If I was doing this for a test, I would simply go 4 times 6 is 24. A squared times a is a cubed. B to the 1 times b to the 3 is b to the 4. And I'd get full marks in one step. Okay, let's look at F. We need to simplify first the top, then the bottom, then reduce. So there's an order here. We've got to deal with the top, we've got to deal with the bottom, and then we'll reduce them. So the base is 5, the base is 5, so there's 6 of them plus 7 more, so that's 5 to the 13. The base is 5 and it's 2 to the 3 to another 3, so that's an exponent of an exponent, so that's 5 to the 9. So we've simplified the top, we've simplified the bottom. Now where are there more 5's? On top. How many more? Once we reduce them, there'll be 4 left. Or you can do the subtraction, 13 minus 9. Okay, our base now is a fraction. Not a big deal. What this means is it's 1/3 squared times 1/3 squared times 1/3 squared. The bases are all the same, so it's going to be 1/3. I had 2 of them, plus 2 more, plus 2 more, is 1/3 to the 6. And just so that if we see this in the homework, you know what's happening, this is the same as the 6 going to the top, or the 6 going to the bottom, because it's 1/3 times 1/3 times 1/3, dot, dot, dot. So that there's 6 of them in total. So that would be 1 to the 6 over 3 to the 6. Well, 1 times itself is 1. So that's another way to write this. So what we've determined is 1 over 3 to the 6 equals 1 over 3 to the 6. Next, 28 divided by 7. I look at the numbers first, and I notice that 1 7 goes into the bottom, 4 7s go into the top. Look at the x's. I have 6 x's on top. I have 2 x's on the bottom. That'll leave me with 4 x's on top when I do 6 take away 2. Y to the 3 take away y will leave me with y squared. The base is 1/2 to the 8th. The base is 1/2. This base is 1/2. So the rule is we're going to take 8 on top and subtract it with 4 on the bottom. And it's going to be 1 over 4 to the 4, which we know means 1 over 4 times 1 over 4 times 1 over 4 times 1 over 4. So there's 4 of them. So it'll be 1 to the 4, 4 to the 4, and 1 to the 4 equals 1. So that's a way to write this, or that is a way to write this, and both work. Okay, let's look over at 6.2 now. Let's put integers with our exponents. So integers are going to cover all the negative numbers and 0. So we need to talk a little bit about negative exponents with an integer base. So what does it mean when I have a to the negative n, where n is a number? Well, it equals 1 over a to the n. So an integer base raised to a negative exponent is equal to the reciprocal of the base raised to the corresponding positive exponent. What that means is 4 to the negative 1 equals the reciprocal of 1 over 4 to the 1, which would be 1 over 4. Negative 6 to the negative 3 will be equal to negative 6 to the 3. So these are the reciprocal, okay, the reciprocal of the base raised to the positive exponent. Now, I'd sort of like to show you why that's going on. This note hasn't really provided that, so let's take a quick look. Let's say I have 4 to the 5 over top of, let's say I have 4 to the 3 over top of 4 to the 5. Well, that would be 4 times 4 times 4 over top of 4 times 4 times 4 times 4 times 4. 1, 2, 3, 4, 5 on the bottom, 3 on the top. If we reduce, we end up with 1 over 4 times 4, which is 1 over 4 squared, which is great. If we use our rules, however, we end up with 3 minus 5, which is 4 to the minus 2. And since these are both equal to each other, that means that 4 to the negative 2 will equal 1 over 4 squared. And that holds true no matter what the base is. If I have base to the negative n, it'll equal 1 over base to the n. And that's the idea of the reciprocal of the base, but with the positive of the exponent. We'll do lots more examples. So, what if it's a fraction then? A over b to the negative n will then be b over a to the n. I can show you why that works. If we follow the same rule up here, it would look like this. So it's the reciprocal, 1 over 3 to the 5, so that's the reciprocal of the base with the positive exponent. Since it's 1, there's no point in having it, so that would simply be. What this means is 1 divided by 3 over 5. What that means is 1 times 5 over 3. And what that equals is 5 over 3. So notice how it was 3 over 5, and it's now equal to 5 over 3. And that's what's here. So if I had a different example, let's say 2 over 7 to the minus 1, that will work out to 7 over 2 to the positive 1. Okay? And 0 exponents. Any non-zero integer base, so the base has to be non-zero. Any base that's non-zero raised to the 0 is equal to 1. Always, always, always. I can show you why. If I had 4 to the 3 divided by 4 to the 3, you would say that that's 4 times 4 times 4 divided by 4 times 4 times 4, which is, if we reduce, is equal to 1. But if I use my rules of subtraction, so following the same argument that we had before, nothing's wrong here, everything's right. So 4 to the 0 must equal 1. And that holds true for any value. So if 126 to the 0, it's going to equal 1. Anything a to the 0 equals 1, as long as a is not 0 itself. So those are some new rules for us to practice. Let's look at some examples. Example 1. Represent each of the following as a power with a negative exponent. Use the smallest positive base possible. So this is 1 over 25. Well, first I need to raise it as a power. The easiest one, to be honest with you, is 25 to the negative 1. And that satisfies this. It represents it as a power of negative exponent. But it's not the smallest positive base. The smallest positive base here is 5. 1 over 25 is equal to 1 over 5 squared, which means that would be 5 to the negative 2. So even though this is an answer for the first part, this is the answer that they're looking for because it has the smallest positive base. 5 is smaller than 25. Okay? The same is going to happen here. The actual, just writing it as a negative exponent, this would be good enough. But it's not the smallest positive base. So we need to find out what that is as a base. And it turns out it's going to be 10 to the 3. You can check that on your calculator. Just do 10 squared and that's 100. 10 to the 3 and it's 1,000, so it works. So we know that that's going to be the case. So 1 over 1,000 is equal to 1 over 10 to the 3. Now 10 doesn't have a smaller base that it can be broken into with exponents. So this is simply going to be 10 to the negative 3. And that's going to be the answer that they're looking for. Example 2. Use the exponent rules to simplify each of the following. At each step of your solution, keep your expression in power form. So no calculators again. So 5 to the 3 times 5 to the negative 4. So we think about that. And what that's going to mean is that if the rule is to add them, you would have 5 to the 3 plus negative 4, which is going to give you 3 minus 4. Oops, sorry, that's a 5 on the bottom. So 3 minus 4, 5 to the negative 1. Now, we usually don't have our answers with negative exponents. They often give us negative exponents, but our answers we like to have only positive exponents. So we would change that to an answer of 1 over 5. Now, there's lots of different ways to do this question. Here's another way that's kind of interesting. What if you changed it to this? 5 to the 3 times 1 over 5 to the 4. Because that's what this is, right? In which case, this would become 5 to the 3 over 5 to the 4. In which case, how many 5s are there on top? 3. How many 5s are there on the bottom? 4. So when we subtract them, where are there going to be 5s left? On the bottom. And we write that. I would leave it like that. That's a positive exponent. Or, if you wanted it with a negative exponent, it means the same thing. Okay, the next one. 3 to the 4 over 3 to the 7. Well, where are there more 3s? There's more 3s on the bottom. How many more? So this is going to give me 3 to the 3, which is 3 to the negative 3. Now, this is with negative exponents. The best answer is going to be, because they're going to want you to have positive exponents. And by the way, this is equal to, as we've seen earlier. So, what are we showing here? We're showing that 1 over 3 to the 3 is equal to 3 to the negative 3. 2 to the 5 to the 0. Well, any base that's not 0 to the 0 equals 1, including 2 to the 5. So I'm done. 2 to the negative 2 times 4 to the 5. So we're going to deal with the top, deal with the bottom, then reduce. So the top is going to be 4 to the 3 over top of 4 to the 6. How do I know that? Because this is 4 to the negative 2 times 4 to the 5. So if I add the exponents, it's 4 to the 3. Where do I have more 4's? On the bottom. And that is equal to, we would leave our answer like that, or if we want a negative answer, that gives us negative exponents. Example 3. Simplify and then evaluate. So now we're going to get a final answer. Notice that this is addition and not multiplication, so you cannot use the exponent rules. That's addition. It's not multiplication. Your exponent law is for multiplication. So this is 2 to the 3 plus 1 over 2 to the 4. Not a lot you can do here. The most you can do is, there's not even any simplifying we really can do. You can try to get a common denominator, but I don't see any value in that. This will be 8 plus 1 over 2 to the 4. 1 divided by 2 to the 4 is going to be 2 times 2 times 2 times 2, so that's going to be 4, 8, 16. And our final answer will be 0, 6, 2, 5. Done. So, not pretty. That's the best we can do. Again, this is negative. You cannot use exponent laws. It's subtraction. So the best we can do is 3 to the 0 equals 1 and minus 1 over 3 squared, which is 1 minus 1 over 9. And so this is easier to do in my head, I think. 9 over 9 minus 1 over 9 is 8 over 9. And if I want it as a decimal, which I wouldn't, I'd keep it as 8 over 9, it would be approximately equal to 8, 8, 8, dot, dot, dot. I would keep it as 8 over 9. We can use the exponent laws, because that's multiplication. So it's negative 2 to the 1, that's what that is, times negative 2 to the negative 4. The bases are the same, so we add the exponents, which is negative 2 times negative 2 times negative 2, which is negative 1 over 8. And again, you can do a decimal if you want, but I'd prefer not. I like the fraction. And the last one, this is a power to an exponent, so we can use exponent laws. So it's going to be negative 2 over 3 to the 2 times 6. That's the law that we came up with for a power of a power. So it's going to be negative 2 over 3 to the 12. So it's going to be negative 2 to the 12 over 3 to the 12. That's going to be a pretty ugly number. Negative 2 to the 12. Now be careful with your calculator. With that negative, it's inside the brackets. So it's going to be 12 negative 2's. Well, 12 negative 2. 12 negatives is going to be positive because it's an even number. So 2 to the 12 will be 4,096. And 3 to the 12 is going to be 53141. And you know what? Those are just ugly numbers. I'd leave it alone. I'd leave it like that and move on. You can get the decimal if you want, but that's pretty good. Okay, guys, that's it for me. I'm going to have some work from you to do from your textbook. Keep your eyes open for any virtual classrooms and come if you have any questions, and we'll stop there.